Hi, in this video, the goal is to solve the logistic differential equation so that you can see how the general logistic formula is related to it. So right here we have the differential logistic formula, and sometimes you'll see this Kp distributed, so you might see it as this form as well. So these two forms are equivalent. This is the most common form, so you'll see that most often in textbooks and in problems, but it's often disguised in this form, so you want to be very familiar with both. The nice thing about this form is you have the Km, which you'll see why that's significant in a moment. So in this video, what we're going to do is we're going to take you from this form to the general logistic formula, which looks like this. So if you're one of my students, you've already seen this form already, and it's a bit of a mystery as to where it comes from, and we've just practiced plugging in variables and using it in applications. So what we're going to do today is we are going to actually separate and integrate this differential equation so that we end up with this result. So let's go ahead and get started and see how this works. So the first thing we're going to do is we're going to separate our variables. And if you look at these factors, p and the m minus p, these are the factors that have the p variables. So they're going to go on the left-hand side with the dp. We're going to take the dt and put it on the other side, and we're going to leave the k with that dt. So when we simplify this, we're going to end up with 1 over p times m minus p, because we've divided both sides by these factors, equals k times dt. So there's no t on this side, but that's okay. K is a constant, so it's a number like 345.008, something like that. It's a constant, so we can leave it with the dt side. And we are going to now integrate each side. Oh, and I have to make sure I have the dp on this side. That's important. When we integrate the right-hand side, that's not too bad. That's going to be a kt plus c. But to integrate this side, we need to use a partial fraction decomposition. So let's go ahead and do that over here. So if you recall, in the partial fraction decomposition, you need to take each factor in the denominator, which is our p and our m minus p, and separate those. In the numerators, you're going to put constants, and we're going to call those a and b. Now, to do the partial fraction decomposition, we multiply each side by the entire factor. So we're going to multiply by p times m minus p, and every term gets that multiplication. When we simplify that, this left-hand side just becomes 1. The p's here cancel, and the m minus p's cancel on this side. So our result is 1 equals a times the quantity m minus p plus b times p. So now our job is to figure out what the values of a and b have to be, and these have to be constants. So down here we're going to eliminate our variable, which is p, so we're going to let p equal m. If we let p equal m, that's going to turn this factor into 0, which will therefore eliminate the a. So this whole term will turn into 0. So we would get 1 equals b p. But since we're letting p equal m, when we solve for b, we're going to get b equals 1 over m. So we figured out what b is, and then we're going to do the same thing with this factor. We're going to let p equal 0 here. If p equals 0, that's going to eliminate this entire term. We're going to get 1 equals a times, and that's going to be m minus 0, since we're letting the p equal 0. And if we solve for a, we get a equals 1 over m. Now, this usually doesn't happen where both the a and the b are the same thing, but in this particular case it does. So this part of our equation turns into the integral, and now we're going to take these two terms. We get a, which turned into 1 over m over p, plus b, which is 1 over m minus p, and that's dp equals kt plus c, because we already integrated the right-hand side. So because we have common factors here, I'm going to take those and put them out in front. So we're going to have a 1 over m here, and those numerators are now going to turn into 1s. When I take the antiderivative, I'm going to have this factor out in front. I'm going to get the natural log of the absolute value of p plus the natural log times the absolute value of m minus p, and that's going to be my right hand side. I don't need to add a c because I already have the plus c on the other side. So this is what we've got so far. The next thing I have to do is now solve for p because we need to get p by itself. Oh, there's one thing I've forgotten. This is incorrect. Hopefully you can see why and you're checking your work. When you take the derivative, you're going to have the chain rule, and since you have the opposite of p here, you need a negative sign in here to neutralize that. Now we can solve for p. So don't forget that's a really easy thing to forget. It happens often. Okay, so if we're getting p by itself, we need to get rid of the m. So let's multiply both sides by m. So we're going to take and multiply the left-hand side by m and this entire right-hand side by m, which results in, and on the left-hand side we're going to do something that's not particularly obvious. We are going to factor out a negative. In turn, we'll make each one of these terms the opposite of what they are. So if I factor out a negative, I'm going to end up with an opposite of the natural log of the absolute value of p plus the natural log of m minus p. There's a reason we do this. It's so that now we can use properties of logarithms. We're going to rewrite this as the natural log of m minus p minus the natural log of the absolute value of p. There's a negative out in front here, and this can be written as the natural log of m minus p all over p, and we have to keep that in the absolute value sign. We still have the opposite sign here, and on the right hand side we have our mkt plus cm. All right, we're getting there. Now we need to get rid of this negative sign, so we've got the natural log of m minus p over p equals, and we're going to take the opposite of everything on this side. And to get rid of the natural log, we raise everything to the e power, so that's e, and all of this becomes an exponent. The e and the natural log cancel, and we end up with m minus p over p, absolute value of that, equals, and I'm going to use properties of exponents to write this as 2 powers, each to the same base multiplied together. This is a constant because c is a constant and m is a constant, so this in turn becomes a number. I'm going to call that number a. Also, when we get rid of this absolute value sign, you get a plus or minus there. So that part and this part together make a new constant, which we're going to call a, and we're going to bring down the e to the negative mkt. Hopefully you're starting to see that general logistic equation form pop up here. And this becomes m, and I'm going to distribute this denominator. So I'm going to write this as 2 separate terms, m divided by p minus p divided by p, which we can call this 1. So I'm going to add that 1 to the other side. If I add 1 to both sides, I end up with m divided by p equals a e to the negative mkt plus 1. All right, at this point we're going to turn the right hand side into a fraction so that I can use reciprocals to rewrite this. So we're going to take the reciprocal of each side, and I'm going to change the order of this expression, and now I'm going to multiply both sides by m so that we end up with p, and I'm going to write this in function notation, p of t equals m over 1 plus a times e to the negative mkt. So here we go. We have our general logistic formula, and that's a lengthy a lengthy problem, but I hope it made sense. You should definitely go back through it. This is not something you're going to have to recreate for me, but it's always nice to know where things come from. I hope you enjoyed this video.